Hi everyone. Today we're going to be doing the second part of the 12-1 notes. So this is the fourth page in the notes packet. We're going to start by finding the probability of non-mutually exclusive events. Okay, and we'll talk about what that means in a minute. So a student-made target includes two overlapping squares. Assume that a sticky ball thrown at the target is equally likely to land anywhere on the target. What is the probability that the ball lands inside one or both of the squares? Now, we saw in the previous section that with probability and pictures like this, like landing in a specific area, we would need to find the individual areas. Okay, so I'm going to find the area of square A, okay, which is this square over here. So notice we have a 10 by 10, which is 100 centimeters squared. Okay. Then we're going to find the area of the second square, so area of B, which is also 10 by 10. Which gives me 100 centimeters squared. And then the overlapping area is this spot over here. So that's a little 5 by 5 square based off the way it's marked, which is 25. Okay. Now there are two different ways that we could find the probability. So again, we want to land in either this yellow region, okay, maybe you didn't print it yellow, but this area over here, the overlapping region, or over here. So our first option is to add up the individual areas, okay? So that's over here, this first process. Well, if this little piece is 25, that means what's left over in area A would be 75. So I'm adding 75, 25, and then 75. That's the total area, okay? Now notice that we put that over 1200. Well, where did that come from? We needed to find the area of this whole thing is the target, right? Okay. So we have 60 centimeters wide and then 20 centimeters up. Now when I multiply those, I get 1200. So for the probability, I take my successful area, which is this portion, the overlap, and then the bottom portion, and I put it over the total possible area, which is 1200. Okay, throwing this into my calculator, I get 7 over 48. Okay, I'll show you guys again how to reduce a fraction. If you had written your final answer as 0.1458 or 14.58%, that would totally be acceptable. I know a lot of the directions in the homework hasn't been specifying. You can always leave it as a fraction if it's reduced, or you can write it as a decimal fraction, okay? Now, if I did want to reduce this fraction, the shortcut in the calculator is hitting the math button and then frac. Notice that reduced my fraction to 748, okay? Now, the second way to find the probability without having to do subtraction, remember we had to do a little bit of backward thinking to get to the individual areas over here. So instead of having to worry about the separate areas of A and B down at the top and at the bottom, we can just use the work that we already did. So I know that the total area is 1200. So this is the probability of landing in A. This was the probability of landing in B. Okay, so notice I have 100 over 1200, 100 over 1200, and we subtracted the area of the overlap. So the overlap was where we were in A and B. You're in both sections. Okay, that's the overlapping section. Okay, most of the time I will tend to use this process just because it usually will be a little bit easier. Okay, and then so when we talk about non-mutually exclusive events, that means there can be overlap. There is overlap between event A and event B. Kind of like this diagram here where you've got A and B in the middle. It's like a Venn diagram. Okay, so that overlap would have to be subtracted because you don't want to count it twice. Okay, so that's the key, is that you're adding the individual probabilities subtract the overlap, so it's not included twice. Okay, so that's the key here. Okay. All right, so let's jump to the next page. And our last type of scenario are called independent events. Okay. So a jar contains 12 green marbles and 8 violet marbles. A marble is chosen at random from the jar and replaced. Another marble is chosen at random from the jar. Does the color of the first marble chosen affect the possible outcomes for the second marble chosen? Okay, so determine the probabilities for each choice to decide whether the first marble chosen affects the possibilities for the second marble. Okay, now if we think about, so we're pulling marbles here, right? So our first choice, okay, we've got this jar and it has 12 green and 8 violet. Okay, so the probability of a green marble would be 12 out of 20 because the total is 20 marbles. Okay, which will reduce to 3/5. Okay, the probability of a violet would be 8 out of 20, which reduces to 2/5. Okay, now what's important in this problem is that there's replacement. Okay, we replaced whatever marble we pulled so that means we put it back in the jar. What that means is your second choice, the second time we go in to pull a marble, nothing changes. You still have 12 green and you still have 8 violet. Okay, so notice that the probabilities didn't change. Okay, so the color of the first marble chosen does not affect the possible outcomes for the second marble chosen because the sample space stayed the same. Okay, and that replacement was the key. Okay, so two events are independent events. They're independent if and only if the occurrence of one does not affect the probability of the second event. Okay, so it could be a situation like this where we have replacement, or we could have a situation where the two events are just unrelated to each other. So let's see a couple examples here. So a jar contains 12 green marbles and 8 violet marbles. A marble is chosen at random and is not replaced. Okay, so let's see what would happen. So Another marble is chosen at random from the jar. Does the color affect the possible outcomes the second time around for the second marble? So here's the first, here's the second. So the first time we have 12 green, okay, and we have 8 violet, okay. So that means the probability of green is 12 out of 20, probability of violet is 8 out of 20. Okay, we could reduce the fractions, but I'll just leave that alone for now. Now, the second time, let's say we pulled a green marble, okay, for example. So we have a couple different options here. We're gonna say option 1. Okay, if I pull a green marble and I don't replace it, that means I don't put it back. That means I'm only gonna have 11 green and still 8 violet. Or, conversely, if I have option 2, what if I pulled a violet? Okay, if I pulled a violet, I still have the same number of green, but I have 1 fewer violet. Now we can totally see that our probabilities are changed. Okay, so now our probability here is going to be 11 for green out of there's 19 total. Okay, that's a different fraction than 12 out of 20. Okay, the probability of violet would be 8 out of 19, which is not the same as 8 out of 20. Okay, and you can even compare the decimals if you're not sure about the fractions. If I do 11 over 19, compare it to 12 over 20, comparing it here, these decimals are slightly off from each other. Okay, so I don't necessarily have to do all this work. To be honest, if you guys just saw the part that said not replaced, okay, that means that the probability is changing, okay? So this means that that the color of the first marble chosen, does it affect the possible outcomes? Yes, okay, so these would be dependent. The second marble depends on the first, okay? Second marble depends on first. Okay. All right, let's take a look at the next one. There are 10 cards in a box, 5 black and 5 red. 2 cards are selected from the box, 1 at a time. A card is chosen at random and then replaced. Another card is chosen. Does the color of the first card affect the possibilities of the second card? And again, we're looking at this portion over here. So if we're pulling 2 cards and we are replacing the card after each pull, okay, so let's say I pull a black and I put it back, our sample space stays the same. So we're gonna say, no, they're independent, because the card was replaced after it was chosen. Okay, so the key is that replacement means independent, not replacing means dependent. Okay, actually we can write that down. There we go. Okay. All right, let's jump to our last page of actual notes. Okay, so we've got a little chart here, the probability of independent events. So if A and B are independent events, remember that means one event does not affect the other. Okay. If we can find the probability of both things happening, so probability of A and B, by multiplying the two probabilities. Okay. Likewise, if you have the probability of two events equal to the product of the individuals, if you multiply the two, that means that they're independent. So, for example, there are 12 possible results from the independent results rolling a number cube and tossing a coin. If you roll a number cube, okay, whatever you get here is not going to affect whether you get heads or tails on the coin. These have nothing to do with each other. So the probability of rolling a 4, let's say, would be 1 out of 6 because there are 6 sides and the 4 is only on one of the sides. And let's say tossing a head, okay, would be 1 out of 2. So in order to find the probability of rolling a 4 and landing on heads would be 1/6 times 1/2. We would multiply the two probabilities and we get 1/12. Okay, so let's do a few examples together. So Alex cannot decide which shirt to wear today, so she chooses one at random. I wasn't sure if you guys have color printers, so I wrote that the first shirt is yellow, this one's blue, this one's yellow, this one's green. The probability of rain today is 40%. Let's say she watched the weather, and so it's a 40% chance of rain. What is the probability that Alex chooses a yellow shirt and it does not rain? So that would mean that the probability of no rain would be what we call the complement of this. We saw that in the previous section. We would do 1 minus the 40%, which is 60%. Okay, so that's 3/5 if we wanted it as a fraction. Okay, and you can put that into your calculator if you want to get the fraction. So we want the probability of yellow and no rain. Okay, so that would mean we've got to do the probability of yellow times the probability of no rain. Okay, now the probability of yellow, well, there are 2 yellow shirts out of 4 total, so that's 2/4. The probability of no rain was 3/5. Okay, and multiplying these gives me 6/20. Pen's running out of ink here. So we get 6 out of 20. If I wanted to reduce this, I'm going to divide each number in half. So we've got 3/10. Okay. I'd be okay with you guys writing it as 3/10, or if you want that decimal, it's 30%. Okay. All right, so what is the probability that Alex chooses a yellow shirt and it does not rain, or that Alex chooses a green shirt and it rains today? Okay, so notice we have this word or in between. So we've kind of got two things going on. We already figured out the probability of her choosing the yellow shirt and it does not rain. That was up here, okay? So we know that this one's 3/10. Okay, now let's do this one separately. So she chooses a green shirt and it rains. So green is 1 out of 4. Raining is 2/5. Okay, so this gives me 2 out of 20, which is 1 out of 10. Okay, so I just found the individual individual probabilities. Now, remember that when we're talking about that word or, okay, so let's call this first event, we'll call this A. Let's call the second one B. Okay, so we want the probability of A or B. Okay, now if we think back to our previous lesson where we talked about an or probability, okay, what happens if A happens or B happens and there's no overlap? Okay, so notice that not raining and raining cannot both happen. Yellow and green cannot both happen. Okay, so to find the probability of A or B, we do the probability of A plus the probability of B. Okay, this is from earlier in the week, okay, the first section of notes. So I would add these two fractions together. And I get 4/10, which reduces to 2/5. Okay, so try to look at these scenarios as entire individual events. So the first probability, yellow shirt does not rain, that was our first option, or the second option, okay? And then once you find those individual probabilities, you can find one or the other, okay? All right, our last example here. You spin the spinner 2 times. Assume the probability of landing on blue is 1/3. And so here we've got 1/3 and here we've got 2/3 on orange. So what is the probability of getting the same color both times? Okay, so what we want is the probability of blue and blue. Okay. Or we could get the probability of orange and orange. Okay, those are really our 2 different options. So the probability of blue and blue, spinning blue once and then spinning blue again, those are independent events. Because if you spin blue once, you totally can spin it again. Okay, the probability doesn't change. So I'm going to have 1/3 would be the probability of the first time, and then 1/3 would be the probability the second time. Okay, remember this is and, that means we're multiplying. So this gives us 1/9. Okay, now the probability of orange and orange, well, we've got 2/3 times 2/3 would be 4/9. Okay, so we want to know what is the probability of one of these happening. Okay, so consider this event A, consider this event B. So we want the probability of A or B. Well, again, from earlier in our section, we would do the probability of A plus the probability of B. Okay, so I would take these 2 fractions, 1/9 plus 4/9, and that equals 5/9 would be the probability of either getting blue and blue or getting orange and orange. Okay, so we're kind of combining our independent events, okay, because they are independent, and we're combining it with mutually exclusive events. Okay. All right, so the very last page, there's no work on here. It's just a little chart that kind of shows you some different scenarios and some, definitions and things like that. So you can use this to help you guys as you're going through the homework, okay? So homework is posted. It's going to be due Friday night by midnight. So because of the change in the weekly schedule, I'm giving you guys the whole weekend to do the quiz. So make sure you guys do it. I will be sending email reminders. All right, guys, that's all I have for today. Have a good one.